Hello each and everyone, my name is Karras. Today I will be presenting the paper Global Graph Clustering and Local Graph Exploration for Community Detection in Twitter. This is a joint work with Aristeidis, Karras, and the professors Ioanna, Giannoukou, Konstantinos, Giotopoulos, Dimitrios, Tsolis, and Spyros, Sioutas. Starting off with the outline of this presentation, first we will see some introductive elements about graph clustering and some of its usages. Next, we'll go through the preliminaries and basically the two methods that we implemented, the global spectral clustering and the local graph exploration. In the third section, we will go into further details about these two methods and how we implemented both of them. On the fourth section, we will discuss the experimental results and their findings, and finally, we will discuss some future directions of this work. So starting off with introduction, graph clustering, which is the segmentation of a graph into groups based on similar nodes. This has come to prominence during the past few decades. This is because of the enormous datasets in the consumer and social networks. So as these datasets increase, there are methods that try to assess that matter, and graph clustering is one of them. So it has become a useful tool in order to recognize communities in social networks or to discover structures in high-dimensional datasets, and in order to construct complex recommendation systems. One specific definition of similar nodes is to split the graph vertices into sets with low conductance. We will discuss more details about that in the next couple of slides. Starting with the spectral clustering is a global technique that utilizes the eigenvectors and the eigenvalues of the graph Laplacian to discover groupings of well-tied nodes. So there are several approaches to perform this task using the spectral information of the Laplacian. The eigenvector, which is associated with the lowest non-zero eigenvalue of the Laplacian of a connected network, defines a near optimal low conductance cut. We will discuss about that in the methodology. So this leads to an iterative technique that splits the graph into several clusters, and theoretical recovery guarantees are obtained based on the conductance between clusters. We will use that as a metric in the experiments. As per the second technique, which is the local graph exploration, the objective here is to get eigenvector-like information by performing just local graph walks, while the embedding of the eigenvector specifies predicted communicating durations among connected nodes. These correlations help us to examine local network structures for eigenvectors approximation by using locally biased random walks. So the objective of a local technique is to outperform global methods in terms of execution speed, particularly for sparse or very sparse graphs. One method is the approximate personalized PageRank, which is also known as APPR, which fulfills this matter by identifying clusters with theoretical guarantees by spreading mass from a seed set, so by splitting a seed set into very subsets. Starting off with the first method, to represent the eigenvector embedding, consider the problem of partitioning the vertex of a graph G for VE into two different clusters, C, which is subset of V, and its complement C prime C as a subset of V, such that the conductance phi C is a minimum over all partitions. So formally the aim here is to solve the NCAT problem, which is shown as equation 1. So the minimization problem can be represented as a constrained minimization of the Rayleigh quotient R, the Laplacian product L d minus A. So the indicator constraint makes the minimization problem here as NP hard. So it's reasonable to consider relaxing this matter to minimize over a subspace of real valued vectors with knee dimension. So this leads us to a minimization problem in linear algebra, where the minimization of the RQ leads us to the solution by calculating certain eigenvectors of L. So the aim here is initially to calculate those eigenvectors. In order to calculate the eigenvectors of the LS, the sparse Hermitian eigensolver named IDish is utilized, which is available in the library of spicy sparse linear algebra. So the eigensolver employs the implicitly restarted launches method, also known as IRLM, which is supported by the ARPAC library. So this can be viewed as repeated applications of a truncated implicitly shifted QR algorithm directly to the three-diagonal matrix produced by the Lazarus factorization. Generally, dense matrices are anticipated to have a complexity that is approximately O(n) squared, because the matrix vector product is the major cost inside every iteration. The predicted complexity for scaling for the Laplacians recorded in a sparse format with a limited number of non-zero values is approximately O(n). Here we have the spectral clustering method, the first method that we use, also named as eigenbed. We have the steps here, and the proof of this method and all the iterations that happen in order to perform the spectral clustering algorithm. There are extensively presented in the paper, so we cannot cover it due to time limitations, but here we have the four steps, the four major steps. So initially we compute the degree matrix D associated with the graph G. Then we compute the eigenvectors of the generalized problem, and we construct a matrix X as in step 3, and we perform k-means clustering to partition the points into clusters. As per the second method, here we use the approximate personalized PageRank algorithm in order to cluster graphs. So this method improves on prior Nibble method that uses a sequence of random walk vectors. A PageRank vector can be described recursively, so this method can consider a simple PageRank vector in place of a sequence of random walk vectors, while it retains theoretical guarantees. So the personalized PageRank method is defined as a unique solution to equation 2, where A belongs to the set 0 to 1 is named as a teleportation constant, where basically the customized PageRank defines the distribution of nodes from a random walk, where the user is transported back to the beginning node S with probability A at each step. So this is a method for local graph exploration without needing to traverse too far to the graph. As per the experimental results, here we have the overview of the experiments. We assess the two methods that we previously discussed, the local and global algorithms for recovering the ground truth in the planted partition model. So the planted partition model is a generalization of the Erdos-Renwi random graph model, which is famous, in which communities are planted within the node set. So specifically, this is another proof that's extensively presented in the paper, but we cannot cover it in detail due to time limitations. So let K represent the number of communities and NO represent the number of nodes included inside each community. Therefore, all communities have a size of NO and the graph has KNO nodes. Let P represent the probability of an edge between nodes belonging to the same group, to the same community, and Q represent the likelihood of an edge between nodes belonging to different communities. Here we have the cluster conductance, which is basically how well knit or how tight is the graph, or how fast a random walk on the G graph converges to its stationary distribution. We have three figures where basically we have the mean conductance of calculated clusters after we deploy our method, our first method. We perform the spectral clustering on the left-hand side figure, while on the center we perform the local PageRank algorithms in the planned partition model with 50 vertices and 3 communities. And on the right-hand side we have the conductance varies as a sign of low cluster quality. Here we can observe that the ability of spectral clustering and PageRank is compared for partitioning in order to find low conductance clusters. The eigenbed method appears more robust across all experiments compared to the local graph exploration method. As you can see, especially on the figure on the middle, the PP-rank method, which is the local graph exploration, has starts with low conductance and then it decreases, while the ground truth is up here, so it's they are far away. Generally, we observe here that the eigenbed method outperforms the local graph exploration method. Moving on to the second metric, which is the F1 score, which is the harmonic mean between precision and recall. On the left hand side, we have two communities of 50 vertices, and on the right hand side, we have three communities of 50 vertices. So here, the spectral clustering technique, the eigenbed method correctly recovered clusters up to Q approximately to 0.35, as you can see here with blue highlighted color. This method went really well as per the F1 score and the performance, while the local graph exploration has poor performance compared to the eigenbed. So in fact, what happens here is the eigenbed clusters 150 nodes into three balanced communities, while the PBrank consistently partitions 150 nodes into two balanced communities, as we can see here, and then it further subdivides one of these communities, providing lower mean conductance than the ground truth clusters. As you can see here, where we have three communities, the eigenbed method again started with high conductance, and then after 0.25 score of Q, it went lower and lower, but still it outperforms the PPRank method. And here the comparison is of course greater than the previous example. One last metric is the computing time, as we can observe. So we compute the time in trees, and we compute the time in sparse graphs. Here we have the average computation time over 20 trials in order to split sparse graph into two clusters. We use this method to do so. On the left hand side we have a single tree, and on the right hand side we have two tree edge sets which are added together. At this point, sparse graphs are considered, since this should be better to reflect the strength of the PageRank clustering method. As you can see, the PageRank is better as per the average computation time compared to the spectral clustering, which required more time to do so. And on the right hand side, once again, the PageRank was the performance was stable, but this is because we increased the phi value and the Q. The time increased once again. But this also represents that the PageRank is more suitable for clustering via local graph exploration. So in this case, the PageRank is more competitive with spectral clustering, but still increases faster as n increases. That's what is depicted here. This might be reduced using a more optimized implementation. In conclusion, in this work, we implement the global spectral clustering method along with a local PageRank based technique in order to perform graph exploration. Generally, the PageRank clustering tends to create one cluster which holds half the nodes and two clusters which contains 1/4 of the nodes for three clusters in the planted partition model. In accordance with the above statement, the theoretical guarantee for the PageRank clustering seems to be poor, as we previously saw. On the other hand, the other method, which is the eigenbed, seems to be more robust and optimal as per the computation time, F1 score, and mean conductance. Basically, the PPRank outperforms the eigenbed as per computation, but overall the eigenbed outperforms the PPRank, which is the local graph exploration. And lastly, one future aim is to modify the PPRank method to whether see if we can reach an optimal spot where it outperforms the eigenbed method across all three metrics. That was pretty much it. Thanks for your attention.